I'm Scott Monroe. I'm a person responsible for product definition of CAN transceiver products at Texas Instruments. Have spent many years in the industrial and automotive CAN space as well as the industrial Ethernet space. So today we're going to talk about solutions for CAN and CAN FD in a mixed network topology. So when we go out to customers, one of the first questions we get is, what is CAN FD? And we get through the basics of what is CAN FD. They ask, can I use it with my CAN nodes? And that's one of the big gaps that we see. I think most of you are probably familiar with this very large gap that we have out in Arizona. John and I are from Texas. We have a different gap. This one more explains the difference between CAN and CAN FD. So if you're familiar with Big Bend, we have Mexico on one side and Texas on the other, and we don't always talk together. So this is one of the challenges that we get into quite often with this discussion. So a lot of our customers, they want to go out, they want to get the benefits of FD sooner, or at least partial benefits of FD sooner than actually getting all the nodes ready and converted over. So we see that CAN FD, it promises to revolutionize the data rate and the frame links in CAN networks, but this lack of interoperability of CAN nodes with CAN FD nodes limits the mixing of these type of devices on the same network. Sure, you can do it. You can run CAN FD and CAN mode, but then you get no benefit. So what we are showing here are some possible solutions with varying levels of system impact and trade-offs. And we see the best possible solutions being sort of a mix of protocol and transceiver improvements. For presentation flow and overview, we're going to present 4 possible solutions. Some of these have been discussed before. A couple of them may be new. Then we're going to talk a little bit about the impacts of the CAN FD controller and PHY handshaking, and then have a conclusion. So the first solution method that we thought about is there are a lot of ECUs, modules out in the field, on vehicles, also in factories. Many of these are actually based on some of the original CAN transceivers. They go back to the days of having a silent mode on the device. Essentially, you add a single mode pin, and what it would do is it would allow the signal path from the CAN bus out to the RxD pin into the CAN controller, but it essentially blocks the TXD path out to the bus. So if we have the opportunity to either build new ECUs or the ECUs that are in the field, if they used the S pin and they're reflashable, we have an upgrade path where we can actually use this and create a new module or a new mode where they can kind of become FD tolerant, so to say. So we use the software, and we basically send a regular CAN message from an FD node out to the network that says all CAN nodes go into silent mode. And then obviously the application software needs to have a delay time to allow all of them to achieve this. And once you're sure that all of the CAN nodes have got their transceivers into the silent mode, you can begin sending CAN FD messages. The CAN nodes will see those and receive those as errors, but they will not get onto the bus because the path from TXD to the CAN is blocked because of the silent mode. Obviously, the drawback here is the node and the CAN node will start having the error counter go up, and you need to trap that. And then at the end, to get the CAN system back into regular communication, it comes back onto the CAN FD node from a responsibility to get the bus back into a state for CAN traffic. Depending on what's happened and how many CAN FD messages you've sent, you may need to clear the error counters, but you can send a CAN message at the end, essentially commanding all the CAN nodes that we're going to switch the bus back down into CAN communication, and then everyone turns their mode back into normal mode, and we start normal CAN communication again. Obviously, it uses essentially hardware that exists today. There's no new invention in terms of that. It's all pretty much on the software and application levels within the system. But one of the big disadvantages is the long latency to turn the bus around from one one communication method, FD, back into CAN. Not the most efficient way to change the communication scheme. So if you don't have enough FD traffic to kind of make up for the time lost when you're switching the buses around, this may or may not be of benefit. But it's obviously a simple and a fairly low-cost way to introduce a mixing of CAN and CAN FD today. A second method that has already been discussed today, and I think has been presented in other things, is to use a sort of new derivative, a partial networking transceiver. So if we use a CAN transceiver with selective wake-up feature and we update the control logic and the frame detection to understand the FD frame, and it can recognize an FD frame, we can make this transceiver so that it will then, when it's in selective wake-up mode, sort of ignore FD traffic, won't increment the error counters, won't do any strange thing. And thus, again, once the software has sent a command out to all the nodes, put yourself into selective wake-up. Effectively, if these are set up to ignore the FD frames, you can block any sort of FD traffic from going through the transceiver, out the receive path into a CAN-only node, and then it's back once again on the FD node's responsibility at the end of the FD traffic to send a command via CAN that matches the detection pattern. So we have the wake-up frame, and then we wake all the CAN nodes back up. They turn themselves back into CAN communication and once again have normal CAN operation. This solution is obviously a more expensive and complicated transceiver, puts more of it in the hardware, and it obviously requires a new system with a partial networking transceiver instead of the possibility to use pre-existing hardware that may be in the field. The third concept we have, and this is something we'd like to introduce for discussion and an idea, is a new concept. We call it a blanking transceiver. Essentially, it's a simple mechanism where we can block the CAN FD messages going to the microcontroller again that is CAN only. And it's based on already known concepts in the Part 2 and Part 5 of the CAN standard. So again, we have two basic modes. We have one which is normal, where we have the bidirectional CAN traffic. So any node can talk on the bus with CAN. And then we have a second so-called blanking mode, and this is for the receiving end of a CAN-only module in the system. So what we do here is in the blanking mode, we basically, again, block the TXD path out to the bus, and we also block the normal receive path in from the bus to the RxD pin, so that when the CAN FD nodes are talking CAN FD, none of their traffic will be seen by the CAN node as an error, and anything they do will not get onto the bus and disturb the CAN FD traffic. What we do here again is, in all of these mechanisms, it's the challenge of how do you tell a CAN node to basically come back to CAN traffic and turn itself around at the end of the FD traffic. So what we've done is added a second receiver that is wired backwards on the CAN bus. So it's looking for an inverted differential signal. So we're kind of introducing a third state on the bus, one that's inverted to what is known as the regular dominant bit within CAN. And then we reuse kind of the wake-up pattern that's known from the Part 5 CAN standard. And then during the wake-up, looking for this pattern, basically it will come out to the RxD pin, and now we have a path to send a different signal to a CAN node to wake itself back up and then go back into normal mode and return to normal CAN operation. So the next part of the question is, how do we actually get this inverted CAN signal out onto the CAN bus? So for the CAN FD side, we need to introduce a way to get a new inverted dominant signal or a differential signal onto the bus. So the first concept that we think about is fairly simple. We know the CAN driver. We can simply add one on that is inverted to the one we know. Similar to Part 5 of the CAN standard, where the wake-up receiver requirements are relaxed versus the main receiver requirements, we could do a similar fashion here with the driver and the receiver, where we aren't trying to actually talk CAN FD time, nor are we trying to necessarily cover all possible systems like 1 kilometers of cable. For cost and implementation viewpoints, we can simplify this possibly, put a reverse driver on, and thus with the reverse driver, when we bring the logic on the mode on this transceiver, which is a blanking and a return to CAN signal transceiver, we can generate a second differential signal that's inverted to the first. This idea also has alternatives. Since we're not talking CAN bit times, we're only trying to get a inverted dominant onto the bus. We can generate that also from an alternative where we could simply pull a CAN line, CAN L, above CAN H through some single-ended type driver and get a alternative method to get a inverted differential signal onto the bus. And then we simply adjust the pattern. It could be a simple single pulse that we look for, or it could be the dominant recessive dominant pattern. That's the more complex one from Part 5 that we could implement at this stage, and then pass the signal out to the microcontroller again that says time to wake up and turn yourself around. So we implemented these discretely in our lab and took some measurements, and our application engineer, John Griffith, is going to go over those results.
Hi, everybody. Good afternoon. So as we kind of just wanted to show a discrete buildup of the system, showing the FD blanking, showing the return to CAN signal, and we built this up discretely using 4 transceivers. So if you look at the left side here, this is the FD capable node. So this node is the one that's capable of sending standard CAN or classic CAN and CAN with flexible data rate. So just like the other systems, this node would be responsible for letting the system know when it was about to return to sending FD nodes. What it would do is it would send out a frame that everybody else would recognize as I'm about to start sending FD messages. These nodes would then toggle the FD blinking pin. So this would be a mode pin. And what it would basically do is it would place the one receiver, which is the standard receiver in low power mode, and it would turn on the other receiver on the inverted CAN receiver. This node would then proceed to send FD CAN messages, and when it finished, it would send the reverse inverted bit that the second receiver would see, and the system would wake back up and return to normal CAN communication. So we want to show this with some signals. So on the left here, this is the CAN node that's sending out. Imagine this is just we did a simplified waveforms, but so imagine this is the frame that's sent out that says, I'm going to start communicating with CAN FD. The receivers on the other side that are not capable of receiving CAN FD messages would toggle their FD blinking pin. They'd go into blinking mode, and the FD traffic could continue on the bus, and it would not be seen by the local node that's not capable of speaking FD. Then, once all the FD traffic was finished and the node wanted to wake everybody else up, actually wait, let me bring back, sorry, 2 things. So this first picture is the FD blinking. So this is the mode pin on the non-FD node. And this is the mode pin on the FD capable node. So once the FD capable node finished sending its FD traffic, the CAN controller would toggle the return to CAN mode pin on the transceiver, and anything seen by the TXD pin would now be sent as an inverted message and not as a standard message. So what you can see here is in orange, this is the differential signal on the bus. So it's sending an FD message with positive differential signal. The return to CAN mode pin is switched, and now the transceiver starts to send inverted CAN bits on the bus. The nodes that are not capable of seeing FD will have the inverted receiver powered up, and it'll see these wake-up pulses after a T filter time, just like Part 5 of the ISO 11898 standard. So if you see up here, CAN high is positive here. Now CAN high is driven low, and the receive signal is seen by the non-FD node. And so we then show kind of a close-up picture of the return to CAN signal. And so just like in part 5, after a dominant signal of T filter or T wake, the RxD pin will be pulled low. The local CAN controller will see a wake-up request has been sent. It'll tell the CAN controller that I need to go back into normal CAN mode, and the system will return to standard CAN. And so I guess we will then move on to the 4th point. If you want to take it. Thank you.
So last but not least, we also look at the managed hub, the bridge, the router. This solution has, I guess, various names that could be used. And in this case, let's assume it's a vehicle or a factory floor. You could insert a new piece of hardware into the system and then break either previous networks into multiple new networks. And for example, add a new FD node with new hardware as it comes along. Obviously, this also adds some challenges. We now need latencies as we route between different networks and more software complexity here at the hub. But it will also provide another method to mix and use FD in existing installations much earlier than converting the entire factory floor or vehicle over to CAN FD. So what we view with all of this, as we're in the middle of this standardization process and we're looking at things, John and I come from the sort of transceiver side of the world, and to put a little bit forward-looking and future-proofing for CAN FD and I would say longer-term physical layer capabilities out there, we'd like to see some better handshaking between the controller and the transceiver. One example of this is Ethernet 802.3. MII is a very basic one, came out of the 100 megabit space and was quite standardized, offers quite a bit of information exchange between the MAC and the PHY. So we kind of use that as an example. It probably has way more capability than we actually need for a CAN system, but there may be a couple of interesting signals that could be used for future PHY development so that we don't follow the path of Ethernet, that a couple years down the road you want to go gigabit and now you get into 5 different sort of gigabit, so you have GMII, RGMII, and all these derivatives. So a couple of the things we see is one, if today this proposal would require the return to CAN signal or any other sort of signaling being generated at the application level and then telling the transceiver to do various things. If it comes out of the protocol hardware of the MAC, there's a more direct change between the two modes and less latency between switching the bus around between which messages there are. The other thing, yesterday there was a question about are there any sort of ideas for reflections and signal integrity at the transceiver level. In the discussion with our Bosch colleagues, we know of a couple of signals that exist within the CAN controller IP that could possibly be muxed to the outside world and made use of with future transceivers to allow adapted behavior during various portions of the FD data frame that could make, I would say, a little bit more future-proofing of concepts that we can use in the transceivers themselves so that we can enable even higher data rates within sort of variable network traffic and have some intelligence within the system because of the handshake between kind of the protocol level and the transceiver level. So in conclusion, we think the future is very bright for higher data rates and larger payloads within CAN systems using CAN FD. In the short term, these solutions offer some options to start gaining the benefits of CAN FD sooner by mixing the networks. The cost versus benefit and system trade-offs, having CAN FD messages mixed with CAN messages need to be evaluated and to determine the best approach for a specific application. And finally, these solutions give various options to balance the overhead, the latency, the software complexity, hardware and cost, which all again need to be accounted for the specific application that you're trying to achieve. And last but not least, TI is committed to CAN FD and isolated CAN FD. Thank you.